Alright, let us summarize the lecture. In this lecture we have learned how to solve homogeneous linear ordinary differential equations with constant coefficients of order n. So we need to set up the characteristic equation, and then every root of the characteristic equation kind of produces one solution of the differential equation. So a real root, we have an exponential function. So a real root of higher multiplicity, we just need to multiply by t squared, and so on, until we have k solutions. Then complex roots. Pair of complex conjugate roots is going to give us two solutions. So one with sine and the other one with cosine. Sine wave and cosine wave. And then if they have a high multiplicity, then we need to multiply by t squared, and so on up to t to the k minus 1. And then if you count carefully, you will see that together, that they exactly account for the number of roots is the same as the number of solutions, and the same as the degree of the polynomial. That was the first theme of today's lecture, and the other theme is Laplace transform. And Laplace transform is a linear transformation from the space of functions to the space of functions. And one aspect of it is that it can be used to solve second order differential equations immediately. So now we treat a second order differential equation together with the initial condition as one problem, and we just solve the initial condition and the equation together. And what we do is we apply a Laplace transform to both sides of the ODE, and then we solve for the Laplace transform of the unknown function, and then we look it up in the table of Laplace transforms. And that's all for lecture 8.